back. So I'm going to sort of be the last guy here. Somebody last night stole my best pictures, mostly gotten from people who were at the same event. But, I prefer my pictures because I'm behind the camera so you can't see me. And if anybody still here tonight haven't been scared away by rumors of dinners, and I need to talk to people who really want to go out for dinner tonight, I have a place in a nice restaurant for 7, but I need a head count now, so if you do that after the talk. And so I was thinking, what do I give for a talk for an event like this? I decided that no, I don't want to give the broad spectrum currency plus talk again. And anyway, I did that for the grad students on Monday, and I thought I could give something about the design of concepts or something, but I don't think a hardcore technical talk would be the right idea. And then I went sentimental. I was going to give a talk called Thanks, just thanking all of my friends. And I thought, that's just too waffly. There's no content whatsoever. So I combined the idea of a slightly historical overview with some pictures. So that's what you're getting. The place is fairly easy taking. We sort of keep drifting to the southwest. If I retire, it will probably be about here, right? But anyway, so for people who are not too good in geography, there's Aarhus, there's Cambridge, where I'm based this spring. The Bell Labs, center of the universe at the time, and now here. So Aarhus is sort of in the middle of Denmark and Jutland. It's a really great place. If you haven't been there, you should find an excuse to go there. That's the town hall example. I love the woods down to the south of town, and there's some very nice beaches. The water is now clean again, and that's the place where I lived until I was 23. With a marker there, and like the picture yesterday, it must have been, it was taken out of Google Street View. You can sort of just go find it, and also you see that, from my perspective, the cars are anachronistic. They weren't that fancy in those days. Anyway, there's the university, the main building, the entry to the main building, dressed up for a celebration. And anyway, I actually worked there, and my main interest at the time in Aarhus, University of Aarhus, was centering about microprogramming, how you could handle machines at the levels or below the usual level of instructions. I was working on instruction set design, looking at machine architecture issues, and I was looking slightly higher on what was known that kinds of machine-oriented languages. That is, things that sort of in the end turned out to be C, but there was a couple of dozen languages designed to work really close to the hardware. Beard's PL360 was an example, but that was targeted for a specific machine. And I heard a talk by Bob Barton, the famous architect from Burroughs, about instruction set design and how to get better productivity, better code by lifting the level of the hardware to give high-level interfaces, so you could have a specific machine for COBOL and such. He'd done the Burroughs 65,000 series before that, which could be seen as an algorithm machine. Had a lot of hardware protection to save you from range errors and things like that. So I was very interested in the OS and hardware interface, and down at that level, even in those days, there was a lot of instructions correctly and got your timing right and memory accesses and didn't overload certain communication path, you could basically do 4 things at a time. At the time, that I thought was very cool. Today, of course, it's fairly standard, but this was 30-some years ago. And I think some of the things I learned here had some impact on my work later. In particular, that was what got me over to England. They had some neater machines in England, and turned out that microprogramming at that level of architecture was actually invented in Cambridge. The other thing that I encountered in Aarhus was singular, and most of what I know about object-oriented programming, object-oriented design, and concurrent programming was taught by Christian Nygaard. He was the guy that invented inheritance and things like that. William Dahl did most of the academic stuff, was into set theory and exact specifications, but he was a visiting professor in Aarhus, and one of the things that I think changed my career was the simple fact that my office was at the bottom of the stairs leading up to the apartment for visiting professors. So once a month, the placement comes rolling into town, and as he comes, he just sort of, before going up the stairs, yells into the office, "Hey, Bjarne, could you find some people and go have a chat?" And then we sat up there and talked for a couple of hours. I couldn't quite understand why he did it this way, but I eventually figured it out. He's a big professor. Norway is a somewhat formal place, at least it was in those days. I can disagree with me if you like. But certainly, you just couldn't sit just arguing with a bunch of students for a couple of hours in Norway. So it comes down there for 2 hours and just gushes out of it. It was great. That's how I learned this stuff. Then in my search for more interesting computers to program, I ended up in Cambridge and found a lot of interesting things. That's sort of the traditional medieval way of looking at it. That's the front page of Trinity College. That's a picture of hunting I took last month. The weather was really weird. It was shirt sleeve or light jacket weather all of March, and then it got cold, and I've been wearing parkas for the last month. That's a picture of Churchill College. That's my college. Anyway, the reason I'm really there is the Cambridge Computer Lab. Got my PhD in there. My office was just under this contraption here. This has been nominated for the ugliest building in Cambridge. But there was a lot of interesting people in there. That's what's important. These days, things are more interesting. There's the modern computer science building. I have an office around the back there, the view down town, and that's sort of the main lobby. Like in a lot of places, they become successful, they have enough money to put on something like that. Here's some old stuff. It all started out a long time ago. When this is Maurice Wolff, who got the second Turing Award for inventing microprogramming, and they built the first stored program computer. Some people mention Manchester, don't do it in this context. Cambridge clearly won. And that was the team. The door behind there is actually framed and sitting in the coffee room in the current lab. Anyway, that's my advisor, David Wheeler. You can recognize him. He's the one without the tie. And a lot of interesting stuff was done there. There's the note in the notepad for the first program to be run, doing a table of squares, 0 to 99. The point is, this is not a test program. This is a complete program testing the whole system.
Sorry, could you repeat off the date?
The date is May 6th, 49. And you can find that notebook. It's on display in the building. David Wheeler was interesting. His way of supervising was I go into him once a week. Full of great ideas, right? You're a PhD student, you have lots of good ideas. That's what you're supposed to have. And I explained them to him, and said, yeah, Bjarne, that's not a bad idea. In fact, it was a pretty good idea, you know. We almost used it at the SAT too, but so he talks for an hour, 2 hours, explain the whole problem area, the techniques involved, why this was a good idea, which I probably hadn't realized, why it wasn't a good enough idea, what you could do instead, and about an hour and a half later, I come up with my ego this big. And after a year, I had an idea he hadn't tried 10 years ago, and that became my PhD. He never told me to do anything. Never told me to read a paper, never told me to write a program, never told me to take a course. That was my problem. You're supposed to be able to figure that out. But the day before I left, he gave me one direct instruction, only one he gave in all 3 years. Keep a high external profile. He was a bit worried that Bell Labs had properties in common with a black hole. Sometimes something comes out of there, but a lot of good people went in, and he was worried about whether I would disappear. So I'll be listening to this. We'll get back to that. There's a lot of interesting people. Roger Needham, very interesting notion in computer science today. We actually need to do something that's useful. And Martin Richards did the BCPL. I was involved in the specification of concurrency in BCPL based on my Simulab experience. And well, there's a bunch of grad students. I got my PhD. Apparently that we had some celebration that day, and the Australian here is very patriotic, so we had to have a picture. Anyway, so there was these 2 Australians, and this was known as a bullpen. There were 7 of us in there. 2 of them were Australians. One was called David Bruce, invariably known as Bruce, and the other one was called Bruce David, invariably known as David. Anyway, let's see. Bruce is a distinguished professor at Amherst, and Dave is a senior or something or other in Google in Zurich.
Most people.
It was an interesting group of people, yeah.
You didn't mean Dave Parker, did you?
What?
No.
No, I didn't. To be honest, I'm not so good with names, and you need to get 5 minutes for me to figure out what his family name was, because of course we never used it. Anyway, so I worked there on concurrency and high-level designs and such, and came over to Murray Hill. That's up here is around the area of the Unix room. This is where all the good stuff happened at the time. Now, the really discerning people were hiding on the 3rd floor down there. Ravi's office was there, I was there, Lego was there, John Bentley was there. But again, the real importance here was the exceptional people that you could run into in the corridors and you could talk to. Dennis Ritchie, Brian Kernihan, my first department head, Sandy Fraser, Lego, and last but not least, Doug McElroy, who saw a letter from him last night. I was very, very touched about that. He is, well, he's the guy, if you have a problem, technically, you go and explain it to him. And even if you've never heard it before, you probably understand the ins and outs of it better than you do by the end of the explanation. really amazing. Everybody goes to him with problems. Just having to explain things to him is helpful, because you know you have to be on your toes. I mean, he invented Unix pipes, for instance, and he wrote the Unix documentation. If you like terse documentation, that's his work. Really great people there. Let's see, Brian is professor at Princeton now, Al is professor at Columbia. Anyway, I was thinking about what to do, and I'd just come out of doing all of this microprogramming and design for high-level support and such. And I got this job, which was do something interesting and tell us next year what you've done. Great deal, I thought that was easy. Especially telling us what you've done. It's supposed to be on one page, right? The old-time great reports. If you can't say what you've done on one page, you don't know what you've done. If you need a whole pile of papers, you clearly haven't a clue what you're doing. So one page. This sounded great. After half a year, I started realizing this was actually different. Because the problem is, what do? I mean, you have a piece of paper on a clean screen, you're going to write a paper, and you get a writer's block. This one is massive, because you can do anything you like, just as long as it's good and useful. And you have good colleagues, so you can get support in any area. Anyway, one thing I thought a little bit about was machine architecture and the directions of technology and such. And I decided that anybody building sophisticated, advanced machines for specific languages, specific operating systems, were going to lose. Because the big guys, IBM, Intel, and such, would always put money in to make Fortran and C run fast. I mean, I wasn't thinking of Fortran and C, because C was not very fashionable in those days, but basically, for instance, the range chain on the Burroughs architectures were expensive, it took a long time to build, and people's old bad programs would run because there was violations in them. They just happened not to happen very often. And so I decided that as long as hardware is getting cheaper at the current rate, clever architects working on high-level architectures, higher abstractions are going to lose. They're going to be wiped out by the next generation hardware. And if they can catch up, there will be the next generation hardware. And until about 5 years ago, this has been true. So what I decided to do was to switch. I still wanted better abstraction, better code, more understandable code. And I still wanted it to run fast. So I went from thinking about microprogramming and building instruction sets. I mean, I built a machine that executed BCPL directly, for instance. I was switching to compilers. You have the same abstraction level, but instead of having the hardware do it, you optimize the bejeebus out of it and runs on a machine that has been optimized for running simple things, like C and Fortran. And so I got the idea of taking C, which has systems programming ability and performance, and code organization comes from Singular. I wanted to build a distributed operating system and simulate aspects of that. This was a little side project that it helped my career, but it was fun. And I wanted a strong, static, flexible type system. One of the observations at the time was people were complaining that static type checking was bad because it stopped you from doing things, and they pointed to Pascal, and I knew from experience, whenever I wanted to do anything interesting, Pascal would stop me. The type system was there to stop me from doing things that Niklaus Wirt didn't like. And, well, I'm not Niklaus Wirt, so I like and dislike different things than he does. And I've noticed that the Singular type system was even stronger, but it never got in my way because it was more flexible. So that was an idea. Elegant and efficient code was what I was after. And very early on, I have some notebooks, and it really Before there was anything, the first day of drafts, there was constructors and destructors. Described as a constructor is what establishes the runtime environment of the member function. Maybe just environment would have been better. A destructor reverses the actions of the constructor. And so the first thing, there was member functions, there was constructors, there was public-private. The next week we had function prototype, basically, and that's where it starts. The idea was to basically create guarantees to make easy to write the member functions. If I have all the resources, if I have all the scopes in place, if I have all the access in place, I can write really simple functions. So in modern terms, establish the invariant, and then you can do it. So that was interesting. And again, a more modern view of what we did was, well, we have some memory. That's bits, just a bag of bits. Constructor makes it into an object. An object has a type and has values in it. And the destructor reverses this process, and out in the other range you get memory again. So here we're in my high-level world that I'd like to be, and here we've got the low-level stuff. And C provided me with the direct mapping to the hardware I needed to this, and the basic ideas about abstraction comes from Singular. And a lot of stuff these days now turns into resource handles. The Kreisler thing is a vector. You have this interface that controls what you can do. Very often the data or the information is somewhere else. This could be the memory for a vector, it could be the mutex for a lock, it could be the file for file and things like that. So this is absolutely it's universal these days. And so the standard code in game modern terms look like this. You have the vector, you have constructors, default constructor, make n elements, make it with an initializer list, destroy the thing again, release any resources. You have some access stuff. You have the iterators for the STL that came many years later, and then you have some little implementation there that's simplified. There's really 3 elements, but they didn't fit on the slide. Some people like this, and well, some people didn't. This one was produced by a fanatical Pascal programmer at Apple. I spotted them and got somebody to take me to his office and ask for one. It's rare to see a grown man blush. Again, I'm sort of weaving modern history into the old stuff. This corridor here, we were at the same corridor. I think Al had moved upstairs by the time. But we had some books that had been written there. And we had them sitting on the wall, sort of near the end of the corridor, just to intimidate visitors. This picture was taken a couple of years ago up at Ravi's place in Albania, and Bentley had the covers. Apparently, when we cleared out of Murray Hill after many, many years, we forgot the covers, the books, and Bentley scavenged them and brought them out again a couple of years ago. And let's see. So I was working with hardware, I was working with abstraction, and you're supposed to be practical and useful. And you know, if you just do things on your own, don't tell anybody, you just as well do Sudoku. So David Wheeler's dictum, keep a high internal profile, means that you have to talk, you have to publish. And it's not publish or perish. My first idea, definitely, for writing something about CV classes, that it was called, was turned down by my department. They said, Bjarne, no, why don't you just wait a year? You can do it better than this, and then you can prove that it actually works, and then it'll be more interesting. I mean, that's not modern academia, where you publish as quickly as you can, as least publish per unit. I was told, get this working right, and then you can ship it. Okay, he was getting popular, and one one day I was sort of leaning up at the door entry to Alejo's office. He was my neighbor at the time, and complaining that people kept asking the same questions, and it was starting to interfere with my ability to work because there were so many questions, and they kept asking the same questions. Now the problem says, you have to write a book. Why? You have to write a book. Write all the answers in a book, then they can read it, and you can get work done. Great idea. Through the management process of Bell Labs, it took me 2 days to get a permission to write that book. And I believe my description was, take these papers that I've written, add water and stir, and you get a book. And that was, I think the proposal was maybe this long as opposed to my summary, but it was that close. So I ended up writing this one. I had a very busy year in, let's be 85, 84, 85. I finished the first version of C++, and I wrote the book, and I finished the compiler, the manual and such. Anyway, so this went around a few places. Then there were people came by from IBM and Sun, HP, and said, would you like to formally standardize C++? And as usual, I'm still working on it, it's not finished, it's not ready. Would you like to standardize C++? It's not ready, it's, well, you know, if you don't do it, we'll do it. Yes, I would like to standardize something else. So, for the next year, we had a negotiation. They thought we should start now. I thought we should start in 2 years. We settled on a year, and in fact, they squeezed in a meeting 10 months later. But in the meantime, I wrote this book, which was basically the description of the language as it was standing at this time. And in the process, I slipped in templates and exceptions which were not shipping at the time, but I thought you just couldn't have a complete C++ without that. So that was another busy year, and this became the base document for the standards effort. And so this book was shared a manuscript among all the compiler writers. And it's not just language rules, there's rationale, and there's implementation suggestions, implementation alternatives, and quite a few things made it into the sort of the mainstream of C++ implementations through this. And this was also the first thing that the various compiler writers could actually communicate. We were setting up a communication mechanism so that somebody, say, at Microsoft or somebody at Sun could actually collaborate in a constructive way. We need a standards committee for that, because otherwise it's a cartel against the law. But if you do it in a standards committee, or even in the preparation to a standards committee, it's a public service. So this is good. We had some talks about redundancy yesterday. I actually love redundancy. This one was written with a very definite aim. Everything important has to be said twice. Because if I screw up, they're likely to disagree, and you can find that I screwed up and you can fix it. If it says it only once, you don't know if it was right or I just screwed up. So I like redundancy in specifications. It can be, there's many ways of doing it, like example and text, or 2 versions of the text, the example and implementation model and things like that. But redundancy is good. Later, I wrote the second edition, which basically is C++ in the ARM days. We're talking about 89, 90, 91, and this got even more popular. As you can see, there's more translations. It's very frustrating to write compilers. Those of you who have done it know, because you never tell users anything they want to hear. There's nothing, and there's you messed up again. And so the few concrete things you get out of this work is this things you write like book covers. The inside of the books is full of code, and you can't show that to your children and your friends, but the covers are good. And then I was asked to give a talk to the ACM conference on the history of programming languages. It's a conference that happens regularly every 15 years, thereabouts. And I took that very serious. I have an interest in history, and I think you should document things. And I then, to write this paper, you know, when you're going to write something new, you go and find what has been done in that field, and you find a model that you can copy. Like that one is copied with not quite enough skill, but with modification from KNR. That's the ideal book for introducing a programming language in a readable way to a large number of people. So I looked for the model. How do you write a paper about the design of a programming language? There wasn't any. There were some papers in programming languages, but they were all over the place. A lot of them discussed the politics of the people, or they discussed the formal specification of the language, and they forget to tell you how they got there, so it's nothing. So I had to write something, and it ended up being the book, Design and Evolution of C++. That is still my favorite book. It is not academic at all. It says things like, yeah, this problem I couldn't solve, this problem I made a mistake, and thanks to these people, and thanks to those, things that you can't write in an academic paper. So this is very nice. I keep getting requests for updating it, but I don't think I'll ever get time to do that. And the third edition got quite a few versions of that one. That's the third edition, and then I added an appendix and a hardcover, and you got the special edition. I wonder what the Germans are going to do, because they decided that this third followed by special was just not regular enough, not proper enough, so they called the special edition the fourth edition. And with a bit of luck, I'll get the fourth edition this year. I wonder what they're going to do. But that's their problem. No. Okay, yeah. I turned out in strange places. That apparently is a building-sized recruiting poster with the Ukraine that one of Yuri's friends sent me. I mean, what am I doing on an electrical media box in California? That one we've seen a couple of times this day. It was, you can blame it on JC. They had a conference in Amsterdam where they had a cartoonist, and now, apparently this is what I'm really known for. I don't know who that guy is. So there's a standards committee, and like every organization, it consists of people, in this particular case, volunteers. So in the old days, before color came to the world, we looked like that. Some of us had more hair in those days, and more beards. But that is the first technical meeting of the standards committee in Somerset, New Jersey. And here we are actually voting the final version of the C++ 11 standard. And no, I don't think Alistair is despairing. He's probably just very tired after a week. The thing that's interesting here, notice we're just sitting up there. There was no computers there. We used paper. So actually there was one computer that was carried by a big guy. Box like this, which was used to take notes during the meetings. That was the only computer. Here, I know for a fact that Mike is communicating with a group of people in IBM scattered over the world. I know that Alistair was communicating with the English group and such. So this is the tip of an iceberg. There are many more people taking part in this paper, in this meeting, than you can see. You can't see me because I'm sitting behind Mike Wong, and I'm not taking the picture. I believe that was a meeting where I was in the Netherlands, right? There was a lot of meetings. That's a lot of travel. To take part in this, if you want to do it seriously, is a serious commitment. 2 or 3 times a year for a week in some place, and if you want to have any impact, you spend a couple of weeks or a couple of months preparing for proposals, opinions of proposals, things like that. But you can see the world this way. I think I missed about 3 or 4 over years. Why do we bother? It's central. There's no owner, no sugar daddy with a marketing budget. We have various implementers. There's a number of implementers that vary up and down. And then there's tool builders and such. Even to have these people meet without getting in trouble with their corporate bosses or the US antitrust laws, you have to have something like a standard process. That's a central forum. It's a place where a lot of feedback comes in, so that's useful. And we're somewhat proactive. Like some people think we're flaming revolutionaries, changing things that should be left alone. Others, like me, think we're moving a little bit too slowly, but we have to have an agreement. It takes a long time. It's a consensus process, and eventually we get there. We need support for mainstream use. The language has to be stable, it has to be standard, otherwise you can't use it. I mean, you can't rely for your basic infrastructure for something that's controlled by the whim of a corporation or an individual. That's very dangerous. So a lot of people want to fit so deep down the infrastructure, they want a standard. And I don't like vendor logging. Standard is about the only way of doing this. There's a lot of interlocking themes. I'll not go through this, but again, here's a view from sort of C++ 98, discussing what's important. Containers, the biggest change in the language for the 98 standard was the standard template library. Alex had to leave early, but that's his handiwork. And also we worked on the exception safety guarantee. I know Matt worked a lot of that, but everybody here that you've heard from the committee has had part in this. We make sure there's no resources leaked. Again, destructors do cleanup. It's all constructor-destructor based. So here we have an example. We have a vector. We have a file handle for a file. We do some work. There's an I/O stream here, and then you throw an exception sometime. All of this has to work right. It does. The constructors established invariants. When you do an operation, you maintain it, and when you leave, resources are destroyed. Notice the wide use of templates here. This is sort of coming in between. I designed templates in 88. By 94, we were getting the STL, and by 98, it was part of the standard and part of what people were doing to some extent. The STL comes out of Alex's work. When he has to characterize, says something like the most general and most efficient expression of an algorithm. Always focusing on algorithms. If you could take the time machine back to the 80s and 90s, there was rah-rah for object-oriented programming. Everything has to be object-oriented programming. Everything has been pure object-oriented programming. Everything that isn't get a lot of bad press. And the definition of object-oriented programming seems to vary by individuals, but very often it means building some huge hierarchies between the virtual functions. Notice there's not very much of it there. The focus on algorithms, separate algorithms from data. A lot of the object-oriented stuff means tying the operations directly to the data. I mean, try clicking your way through one of these point-and-click interfaces if you have forgotten which program it is that is supposed to open this file. It's it's a bit of a pain. The STL isn't like that. Using compile time resolution is essential, and parameterized with policies. So we can have a vector like that, a list like that, and the separation is the algorithms are like here. They communicate through iterators to containers. Containers provide iterators for the algorithms to work with, so it ties in rather nicely. Here's the general model of a stream. You go from the beginning and go this way. If it's a bidirectional iterator, you can go back again. And here's sort of one of the archetypal algorithms from the time find if, from the beginning, unless you have reached the end, and unless you have reached the something for which the predicate works, go to the next one, and if you get out there, return first, which will have been moved to wherever you were. So that's a fairly standard one. You can call this for any sequence of any type, so it's very general. Anyway, that was a question I asked yesterday. I mean, we have a committee design. I don't think so, but the individuals can. So you see too many traces of individuals in the standard, but it's by and large much better than we could button in other ways. The committee works in larger and smaller groups. There's a lot of computers these days. There's Jonathan right there. So there's lots of people involved. We're trying to decide. Oh. No, the battery has